Why are earthquakes so hard to predict? We know they're gonna happen, but we don't know when. Why? You've probably heard of this a lot, especially in the news with all these Iceland earthquakes and volcanoes. But we don't know the answer to why earthquakes are so hard to predict. Well, in this episode, I'm going to be talking to Dr. Ramon Arrowsmith to find out how earthquakes are formed and why they're so hard to predict. Dr. Arrowsmith studies earthquakes at Arizona State University and knows a lot about earthquakes and will help us answer this amazing question. Let's get right into this interview. Let's go. Hello, Dr. Arrowsmith.
Hi there. Nice to meet you.
Yeah, nice to meet you too. Thank you so much for joining me today.
It's my pleasure.
Can you please introduce yourself to listeners?
Yeah, my name is Ramon Arrowsmith, and I'm a professor of geology in the School of Earth and Space Exploration at Arizona State University. And this year I'm actually spending some time in Italy because my wife, who's also a professor, you may have heard of her on an earlier interview, Professor Amanda Clark. We have a sabbatical this year, which means we have teaching relief so we can travel and do more research abroad.
Well, that's really cool. So what kind of research are you doing in Italy?
Well, I'm doing a lot of research that's actually in other parts of the world, but I'm enjoying my time here. And I do have some projects in Italy working on a few of the active faults in this region.
Well, that's really interesting, and we'll get into some more of that science of faults later in the episode. So how'd you get interested in science?
Well, I grew up in New Mexico in the southwestern U.S., and I really enjoyed the beautiful landscape of New Mexico. And I used to go camping and fishing with my father, and we would be out in the mountains, and I just really enjoyed being out and wondering, how did this landscape, how did these rocks get to be how they are? And then also my mother was a teacher, and so she instilled in me interest in knowledge and helping others.
That's really interesting. So what got you into this field of earthquakes?
Well, I went to college in Southern California in the Los Angeles area at Whittier College, and I worked in an aerial photography collection. So it's like a library for air photos, and they were historic. So many of the pictures were of Southern California from the 1930s. And there were very few buildings and not as much urbanization. And so when I looked in the images, I could see hills and valleys and deformed landscapes that were clearly the result of faulting and deformation and past earthquakes. And it was really interesting, kind of intriguing. And then when I was also in California in college and also for graduate school, I was in several earthquakes. There was one in Whittier in 1987. It was called the Whittier Narrows earthquake. But the big one that some people will remember, if they're old enough, was in 1989. There was an earthquake in the San Francisco Bay Area that was interrupted the World Series. So the baseball game was occurring in the Bay Area, and this earthquake occurred. It was pretty strong, and so they stopped playing the game, and everyone was really afraid, and it shut off the power in the region, electricity. And I was a student at Stanford University, and I was in that area, and I felt it. It was really strong. I was taking a nap, and it woke me up. It knocked everything off of the dresser in my room, and made a lot of noise, and was really strong motion. And we just started studying that earthquake, and it was really made earthquakes very tangible for me.
Well, that's cool. You've been through an earthquake and now you're studying them.
Yeah.
Now to get into the amazing science of earthquakes. I'm super excited for this because I myself have never been through an earthquake, and hopefully I won't be through one that's really, really dangerous, but it's still really cool to think about. So what are earthquakes and how are they formed?
Well, earthquake, it's kind of literal. It means shaking of the ground. But when we talk about earthquakes, we usually talk about them in three parts. We say source, path, and receiver. So when we feel the earthquake, we're the receiver of some ground motion that moved or went through the earth to us along some path, and it was produced at a source, which was some slippage or some rapid motion in the Earth's interior. And so you can think of the earthquake source kind of like when you snap your fingers. You put them together and you start pushing them, and you can see them kind of deforming, right?
Yeah.
But you don't know really when it's going to snap, but suddenly it does. And so that's what the earthquake is. It's basically overcoming the frictional resistance of the surface between your fingers and this rapid slippage. And that rapid slippage displaces the rocks around it and produces the seismic waves that go to us that we feel.
So, what makes these earthquakes vary in strength?
Well, it's how it's in a sense how much area slips. So the area between my two fingers would be a very small earthquake, but if we have a much larger area, one like if you think of like a brick sliding over another brick, that would be a slightly larger earthquake, and we get more and more surface area involved that we move across this interface, which we call the fault. The earthquake, the energy increases.
Wow,
And
that's
so
really cool.
when we talk about like people say, oh, it's a magnitude 7 earthquake, that would be a piece of fault that might be, let's say, if I use the metric system, it'd be about 15 kilometers wide or deep, and maybe at least 100 kilometers long. So it's a big piece of the Earth's crust that moves in the earthquake, but that produces a lot of energy, a lot of ground shaking in that same region and beyond.
Now, here's a question that a lot of people have. Why are earthquakes so hard to predict? And are they even impossible to predict? And is there a way to somewhat predict when they're going to happen to keep people safe?
Great question. Well, it's just like you snap your fingers, like they're gonna snap, right? But you don't know when. Like I'm getting ready, and oh, let's slid a little bit. Okay, wait, let me do it. When? We don't know. We know it's gonna slip. We know the loading is there. I'm pressing. I'm making it go, but I can't predict exactly. So it's sort of the same problem. Is that we know where the faults are in general, and we know that the loading is occurring, that we're sort of pushing on the Earth's crust. The springs are, getting depressed, and the rocks want to break, but we can't say exactly when. And that's in part because the strength of the faults is kind of controlled by very small areas on one of these fault surfaces, yet it's a really large fault surface. So we call it has its inner and outer length scales, which means that, it has like a meter that's like the most important part of the fault that's over 10 kilometers. So that's like 1/10,000th of the fault is the most important part. We just don't know which. And so it's quite difficult to predict. And also because for prediction, we want to be specific. We want to say where and when. And if it's to be useful, we need to know better than just random.
Mm-hmm.
And that's hard. Now, what we've tended to do for earthquakes is we change the language. We don't say prediction, we say forecasting. So that releases a little bit or decreases the specificity. And we say, well, it's going to be in this area and it's going to be in the next 50 years, which, for every day in our lives is maybe not that great, but over longer term for a city or for a critical facility that's there for a long time, that might be useful. And we're more likely to be correct if we relax our constraints like that. Now, another thing about forecasting and prediction is naturally occurring versus earthquakes that might be induced by human activity. So one of the things that your listeners might have heard of is fracking. And what is that? So fracking is when we inject water at high pressure in a borehole that was drilled, and we crack the rocks.
Mm-hmm.
And that lets us drain them of oil if there's oil in that part of the rocks that we cracked. But all that water that we use to crack the rocks, and then also when we drain the rocks, there's oil and there's water. We have to get rid of all that water.
Mm-hmm.
So we pump it back down in the ground. And so this adds a lot of weight and increased pressure to the rock. And so sometimes we induce earthquakes. So people who live in Oklahoma and Ohio, for example, are places where there's induced earthquakes. So we're making earthquakes. We still can't say exactly where they are, but we know we're making more of them in those regions. We don't know exactly when they'll occur. And then the final thing about prediction, forecasting, induced earthquakes is earthquake early warning. So this is kind of interesting because we can do this well, is if you think about it, earthquake occurs, seismic waves are moving through the crust. Seismic waves move at a few kilometers per second. So if we convert that to the imperial system, it's like a mile per second. But if we have a sensor that's near the fault and the sensor notices, whoa, I'm moving a lot, it can send the signal by the internet, which is like the speed of light.
Mm-hmm.
And so it can get way out in front of the seismic waves. And computer system, maybe with human help, can say, hey, there's an earthquake occurring, and it looks like it's growing and it's going to affect people in these regions. And so if those people are like 100 miles away, it might only take 10 seconds for us to figure out there's going to be an earthquake. They could have like 90 seconds of warning.
Mm. Oh.
So it's not a lot of time. We call that earthquake early warning. It's been set up in the Western US. So in California, Oregon, and Washington. It's been established for a long time in Japan and in Mexico. And so if you think about early warning, a few things like someone who's maybe in surgery, like if a doctor's doing some
Mm-hmm.
surgery, 90 seconds gives them time to kind of get out of the patient and,
Mm-hmm.
stabilize things. Or of course, nowadays we're all interested in data. So
Mm-hmm.
data centers can stabilize their data systems to know there's incoming ground motions, things like that. So they shut down trains sometimes because of early earthquake early warning. So that's kind of where we are. Once the earthquake occurs, we can tell everybody if they live far enough away. If you live right on top of it, you still won't get
Yeah.
much warning.
Yeah, and these earthquake warnings, we have the age of the internet right now, so it's pretty easy to get these warnings out to lots of people at a time because of
Yeah,
all these emergency alerts and all these things that we get. It's pretty
yeah.
easy to keep people safe, but again, it's only 90 seconds.
Or so. It's tens of seconds, depends
Oh wow.
exactly how far away you are.
Hmm.
Yeah, there's apps now in California. There's one called Shake Alert.
Oh.
People can download it and you opt in to get the messages and it works.
Wow. And you also mentioned that there's some specific locations like Japan, Mexico, and California. Why those locations? Why would those locations have more of these forecasting systems?
Well, because that's where the faults are. That's where, one of the things you might ask is, well, why do we have earthquakes? And I said what they are, but why is a different thing. So we have the slippage on the fault surface, but then so we have ingredients. Then one is the faults, which are these interfaces along which this relative motion occurs. And the second thing is the loading, the forces that are driving this slippage. And a lot of that comes from in the earth is from plate tectonics. So the relative motion of blocks at the earth's surface. And sometimes it's kind of distributed, but in some places it's localized. We call those plate boundaries. So in California, the San Andreas fault system is basically the zone of relative motion between the Pacific plate, which is moving to the northwest, and North America, which is relatively stable. And so along that zone, we're sort of shearing and driving, Western California northwest, and that gives us that loading, that shearing. And so it happens kind of like a movie where each frame is one earthquake, but if you play the movie long enough, you start to see things move.
Yeah.
And same thing, California is this kind of lateral motion. Neither side goes up or down, but just slides. Whereas in Mexico and Japan, we have what's called subduction. So there's convergence and one side goes under the other. And that convergence, that interface, it makes really big fault surfaces, kind of right where my hands are
Mm-hmm.
touching. And that big fault surface means you can get big earthquakes generated. It's also a little bit convenient because a lot of times those faults are a little bit offshore
Mm-hmm.
and the people are obviously living onshore. So that distance between where the earthquake occurs and where the people are is far enough that we can do the early warning a little bit better. They get more warning, like a couple minutes maybe.
Yeah, that's really cool. So you talked about subduction zones, right? I've heard of that somewhere. Let's see, where did I hear about that? Oh yeah, in the episode with Dr. Clark. She talked about subduction zones and how volcanoes are formed with subduction zones and how rocks melt. What do volcanoes have to do with earthquakes? And
Ah,
especially with these things going on in Iceland, we read about volcanoes and earthquakes, but what do those two things really have in common?
well, yeah. So starting with the subduction zone. So, as she explained to you, as we push this one plate down underneath the other, it promotes melting.
Hmm.
And so, but shallowly, before things melt, they still have this frictional strength. And so we get big earthquakes on the upper or shallower part of the subduction zone. And then as we go deeper, then we get to the roots of the volcanic system. Now, the more direct relationship between earthquakes and volcanoes is that the magma, the molten rock that's in the magma has pressure. And so it can drive the earthquakes, just like something has to push my finger to make the earthquake occur. We can have, the magma pressure can basically push open a zone, and it's not empty, it's just full of molten rock.
Hmm.
But as it pushes open, it's going to pressurize or put more force on the um, surrounding rock, and that can drive earthquakes. So, in this case, most recently, there's just the last couple of days, we've been having this really spectacular eruption in Iceland. So, this magma is being intruded. It's going in the crust in these narrow zones to the surface. But as it was coming up, it was pushing, and it was pushing, it was kind of cracking the rocks, and that cracking is the earthquakes.
Wow, that's really cool, and how volcanoes and earthquakes are related, and plus how you guys study the volcanoes and earthquakes, which is really, really cool.
Yeah, and one thing there, just to say, is that that's how we knew that one way we knew the eruptions were going to occur in Iceland is because we have a seismic network that could be, deployed or strengthened around that zone, and they could, identify even small earthquakes in the zone above the sort of rising magma. So they knew, they kind of had a sense of when it was on the move. So in that regard, it's a little bit easier to predict volcanic eruptions, and we use earthquakes to do that.
But you can't really predict earthquakes because they're way harder.
Yeah, I think so. Although Professor Clark, she would say, well, volcanoes are hard too, but uh, earthquakes are a little more challenging because we just don't have any warning. But the the magma moving produces earthquakes, so we can use earthquakes to understand or anticipate the movement of the magma.
So, what new research is being done on earthquakes and prediction prevention technologies?
Well, we just alluded to some of it. So the first thing is just improving our ability to observe earthquakes, and that to begin with is presently. So we have invested in networks of seismometers. So they're quite sensitive instruments that really observe those ground motions, and a lot of times they're the small ground motions that even we as humans won't notice from more distant earthquakes. And so, but if we have a lot of seismometers in a region, we start to get a pretty good picture about where the earthquakes are occurring, how big they are, how often they're occurring, and that lets us just make observations of the phenomena. And then the second thing is other kinds of networks, like we say geodesy. So people have GPS on their phones, or GNSS, so global satellite navigation systems. And just like your phone can tell you, okay, I need to figure out how to drive down the street. Well, if you process the data a little bit better, you can get the position down to less than a millimeter. If you have a very fixed position and you make a few corrections, and so then the plate tectonics is moving the Earth's crust at more than a few millimeters per year in places. So like in California, the west side of California is moving northwest at 30 millimeters a year. It's like the
Wow.
rate that your fingernails grow. So we can measure this with GPS. And so we can, therefore, if we have a dense network of of these high quality GPS receivers, we can get a sense of where the deformation is, and especially where the gradients or the changes in the rates of deformation are, because that means we have some loading that's occurring, and we could have some earthquakes. So those are two technologies. Another technology is we go back in time, and so I don't know if you have you're recording the screen, but you
Yep.
see this line right here behind me. This is the topography along the San Andreas Fault in Central California. And that line is showing the kind of zone of relative motion. Uh, that's the San Andreas. And so we look for cues in the topography like this. So this is high resolution topography, which means we've measured the topography. We have like for each XY position or east and north position, we have an elevation every meter or finer. So very fine scale data about the topography, and that in that topography, we can read the record of past earthquakes. So, the problem with the seismic networks and the GPS networks is they're only, decades long. So, but if we want to go back in time, we use the topography to get a longer record of deformation associated with repeating earthquakes.
Hmm.
So topography is a key one. That's my specific area of expertise. And then the other thing we can do is date the rocks or date the surfaces that are being deformed. So we call that geochronology. So some people may have heard of carbon-14 dating. So if there's some organic material and like the plants or animals die, then we can basically we start to see a meaningful change in the ratio of carbon-13 to carbon-12. And over time, that changes in a way we understand. So after a certain amount of time, we find that organic material, sample it, we can figure out how old that material is, and then we assume that whatever it's contained in, like some sedimentary deposit, is the same age. So we can get a longer term record of this repeating record of earthquakes between the combination of topography and dating surfaces that are offset.
Yeah, it's kind of like making a timeline and then using that, what happened in the past, to predict or maybe even forecast the future.
Exactly. So sometimes they talk about it as like a budget. So I'm putting so much money in, which is like the loading, and then each earthquake takes a little bit out. And so are we staying close to zero in our budget? Usually plate boundaries kind of act that way. So the amount that goes in is released by the earthquakes. Other places it's a little more complicated. So like continental interiors, we might store a lot of energy for quite some time, and then all of a sudden, boom, 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 we'll take a huge withdrawal. And the balance is a little more complicated. But plate boundaries are a little more straightforward in a general sense for this balance of input straining and exported earthquake energy.
Well, that's really interesting how you can use the past to predict the future.
Yeah, that's our forecast. Let's be careful.
Yeah, forecast, because prediction is not really, as of now, it's not really possible with earthquakes.
No, it's quite challenging. We're still looking at how to do it, but it's difficult.
Yep, forecasting the next 50 years.
Yeah. So here's another point about prediction, just some questions that come up is what about animals?
Oh,
Because
yeah.
sometimes people say, oh, well, can animals, do they act strange or something before an earthquake? And there was one example in China in the 1970s where a lot of animals in this one region were behaving strangely, and the officials, people said, hey, these pets are, something's going on. So there was a kind of evacuation ultimately from that region, and then an earthquake did occur.
Oh,
And
wow.
so that was nice. But then, sadly, a few years later, there was another earthquake in a nearby region, and there was no disruption of the pets, and many people died. And so it's not that pets have any different things that they're sensing. It's just that we humans are always, I think, often distracted.
Yeah.
Whereas, like if you think of especially of a cat or sometimes a dog, it's sleeping or napping, and then suddenly it might feel a tiny movement, tiny earthquake.
Hmm.
It will register that and think that it's unusual. So So I don't think that animals have any special sense. They're just a little bit more aware of their surroundings
Yeah.
than we are because they're less distracted. So sometimes earthquakes, like a big earthquake, can be preceded by what we would call foreshocks or smaller events. And those smaller earthquakes then might be felt by either seismometers, seismic network, or pets.
Hmm.
So we're aware of the phenomena of foreshocks, and we do use them to kind of focus our attention.
Well, that's really cool. And maybe we might have super pets in the future that could
Yeah,
predict
exactly.
earthquakes. But
Yeah.
as of now, probably not.
Right.
So, what advice do you have for kids who are interested in science?
Well, a couple things. One is just, science is about being curious. How does the earth work? What's going on? So it's to be curious, and then to go outside. I think that a lot of times outside is, you sort of start to see a little bit more of the natural world, but you can also explore, look at maps. And now with the internet, you can use, like Google Earth or, Google Maps or Apple Maps, Bing, some of these different, and just explore the world looking at maps. That's how one of the places I got started. And you start to see patterns, you think, what is that?
Hmm.
And so just be curious, keep looking. Um, you know, and then, of course, science, don't be afraid of math. It's just a tool.
Hmm.
I always like to say don't apologize about showing
Hmm.
some equations. Just try to understand them. They're just trying to help us, keep track of things. Um, so don't be afraid of math. Uh, Also, understand that science is kind of the idea of testing ideas. So you say, well, I think this works this way. Okay, well, how do we test it? Making a little experiment. And you just go do that many times. So yeah, so be curious and experiment and explore. Those are kind of three key words for the beginning of science.
That's some really good advice. Thank you so much for joining me today, Dr. Arrowsmith. I really enjoyed it. I learned so much about earthquakes, and hopefully, you might be able to evolve some super pets that might predict earthquakes.
Yeah, I hope.
Yeah.
It's nice to talk with you.
Yes, thank you so much for taking the time today. All right, so should we go look at how we can evolve super pets?
Yeah, that sounds to me like that's your next one of your next topics for an interview.
Super pets that can predict
Yeah.
earthquakes. Thank you so much for listening to this episode of Spectacular Science. Spectacular Science produced and hosted by me, Oxygen Raman. Our theme song and additional music are by Chan Ramachandran. Special thanks to Dr. Ramon Arrowsmith for accepting my interview invite. Dr. Arrowsmith, I learned so much in this interview and I had so much fun. Thank you so much. Please visit my podcast website, spectacularsci.com, to find interactive activities, articles, and blog posts. That's spectacularsci.com. Do you have any science questions that you want answered on a Spectacular Science episode and get a special shout out? Well, head over to spectacularsci.com/contact with a grown up and send me your amazing science questions. I'm looking forward to reading your science questions and answering them on future Spectacular Science episodes. Thank you so much. Also, don't forget to subscribe to this podcast and share with your friends and family. Subscribe and share this podcast with your friends and family. Thank you so much. Thanks for listening, and we'll see you on the next episode of Spectacular Science next week. Keep thinking about science.